Does it work now? Yeah, okay. Yeah, so so this is the picture still, and yeah, so what's next? So if you, so obviously this gives you a way of extracting large cardinals from some combinatorial situations. Yeah, so you get a very mild one, zero sharp. So now the hope is that you could somehow repeat the procedure and get more. And yeah, so the next target would be a measurable cardinal. So one can try model L of u. And yeah, so what is L of u? So Hugh Woodin already talked about it. Yeah, so if we have just a normal measure on some kappa in V, so we just construct the relatively to this measure, and we get a model which is a very nice model with a measurable cardinal. But remember, yeah, so it doesn't have this, may not have this entire u in it, just u intersection L of u. And it has nice combinatorics similar to that of L. But it's, for example, the proof of CH is very different in this model than the proof of CH in L, and I will explain later why. But the problem with this model is that if we want to get consistency results, yeah, along the same lines as we saw in the case of L, then yeah, this kind of builds on the existence of a measurable cardinal in V, so that's not really what we want to have. And this is another big problem, yeah, and that has something to do with the proof, for example, of continuum hypothesis in L of u. This is not acceptable. Okay? So zero sharp, so we saw from what I said before, it should be clear that if we have a measurable cardinal, we have zero sharp. So this model has a measurable cardinal, so it has zero sharp, but zero sharp enters the hierarchy very late. Yeah, it enters the hierarchy between those two cardinals. No, you get it before you get the full U, yeah, somewhere. Yeah. It's just condensation if you think about it. Yeah. So you don't need to go past kappa plus, yeah, but so it's somewhere between those two. You get some sufficiently big fragment of U. Yeah. Yeah, and also, yeah, I was a kid when this has been developed, so I don't really know the history, but it looks like really there is a problem if you want to go significantly past. So that's the picture, yeah? This is L on the left side, and this is L of u. So if you go all the way to kappa, yeah, so the U consists of subsets of kappa. So all the way up to kappa, when you are constructing L of u, all the way up to kappa, you are just constructing L. It's a very slim hierarchy. And then suddenly between kappa and kappa plus, it just becomes, you just bump up the width. Yeah? So zero sharp comes into somewhere here. So if you just try to prove the continuum hypothesis, what you do is you just look at some initial segment of your model, which is big enough. Yeah, so say you have a subset of omega. You look at some initial segment which is big enough, take an elementary substructure and collapse everything to countable thing. Now the countable thing will have some collapse of this measure in it. Yeah, definitely not on the hierarchy. So the L proof just does not work. Yeah. So what would work is, again, you have to use iterations. You have to iterate the small structure to compare it, but we will not do it here. I mean, but we will try to see how to build models which don't look like this. Yeah, so the models which are acceptable. So the hierarchy will be kind of more regular. But before that, let's just go back and recall a little bit of history. So what we did with L and 0 sharp, one can a little bit go up with the consistency strength. Namely, once we prove 0 sharp exists, it's a real, we can adjoin it to L, and now the entire theory goes through with L of 0 sharp in place of L. So we get something which is called 0 double sharp, and so on. And Dodd and Jensen did this, and they actually constructed the first model the first model which belongs to the family which today are known the core models. And so K is like L, but it's a relative notion. So what it does, it picks all cardinals, all large cardinal properties you have in V. So if you make an assumption that 0 sharp does not exist, then K is L. But if you allow some large cardinals, then K will pick some property. Then K will just be bigger than L and pick all of these large cardinal properties. One thing, though, is that in order to make the theory work, you always have to make some anti-large cardinal assumption, in order to be able to construct K. And the Dodd-Jensen's assumption was that there is no inner model with a measurable cardinal. And under that assumption, they constructed K and proved those three fundamental properties. That means the covering, which is the same as covering for L. Just you replace L with K. Rigidity, there is no non-trivial elementary embedding of K, which is the same. If you make the assumption 0 sharp does not exist, then K is L, and there is no non-trivial elementary embedding of L, because that embedding would witness the existence of 0 sharp. And generic absoluteness. If you force with any poset P is a set element of V, and you force, then the K which is constructed in the generic extension is the same as K of the ground model, which is very important for many applications. And so now we have all of these things I mentioned before, and I haven't talked about square, so let's just, I guess both Laura and Menachem reminded what square is. So, and I believe it was Solovey who proved, actually in all of you, but so I don't know, so probably Jensen proved along the lines square in K. So the square sequence which comes from K is a square sequence in the sense of V, because we have this. So and then you want to go further, and they go a little bit further, and they got a covering theorem for L of U. But that's where the differences start, because, for example, you cannot have this any longer. You can, because once you have a measurable cardinal, you can do pre-forcing, so you can change cofinalities. But the next substantial step, really upwards, was made by Mitchell, and that involves the notion of Mitchell order. So let me briefly recall what Mitchell order is. If you have two normal measures, one of them is smaller than the other one, if and only if the first one is inside the ultra power. And this is well founded, and it gives you the stronger form of measurability, because if you have, say, if this is true, then there must be still many measurable cardinals below kappa. If you have just two such measures. but also it's just witnessed. So we are still in the range of measures. So we cannot have too many measures. We can have only as many measures on kappa as the size of the double power set of kappa is. So we need a different notion if we want to generate more complicated elementary embeddings. Yeah. And also one can see that just here, so the first step away from what was done before is that if you just cannot, and Hugh was telling something similar with an extender, right? You cannot, this model for L of U is not going to give anything more because of that picture, yeah, we had before. I mean, up to kappa is just L. But if you have two measures, one bigger than the other in Mitchell order, then you must have many measurables below kappa already. So you cannot agree with L below kappa. Yeah? And even more, I mean, you don't really get anything new. Yeah? The point is, yeah, this is iterable. Similarly, as we did with zero sharp, one can prove iterability of this. And once you have iterability, I think it was Kuhnen who proved uniqueness. So, yeah, so if you have any such two models which are iterable, then they are the same. The measures are the same. So even if you have a stronger measure, if you just adjoin it, if you just construct relatively from a bigger measure, you just get the same thing as constructing from smaller measures. So you cannot really get more this way. So the solution was just to build a model relative to a sequence of measures. Yeah? And that's what Mitchell did. Yeah, so first he had some models which were not really fine structural. So as far as I know, it was not clear if GCH could be proven there. But later, he actually, yeah, so, and it was for a while a problem because the way Dodd and Jensen coded measures in their core model, they always coded a total measure. Yeah, and yeah, there was this problem Hugh Woodin mentioned also, that if you are constructing a model from below, at some point you are facing the question whether to add certain measure on your sequence or not. And if you add it, you just add it and you have no control of what's going to happen later. So at some later step, you may add a new subset of the critical point of that measure, so the measure is no longer a measure. And this seemed to be a puzzle for a while. Yeah, so that's what this slide says. Yeah, so you construct from a sequence of measures. Yeah, so this will be models we will be looking at later, just that the sequence will be a sequence of extenders. Yeah, so we are constructing relative to some sequence, and then we add the next object as a predicate. Yeah? But at some later stage, we may unintentionally add a set. Yeah, so at this step, we add a set U alpha, add a measure U alpha. It measures all subsets of kappa which are inside this structure, J alpha of U vector. But later, we may add a subset of kappa which is not here. So this is no longer a measure. We cannot use it to form an ultra power of this thing. Yeah? And yeah, so such a thing would be called a partial measure sequence, and later when we deal with extenders, it will be called a partial extender sequence. And I think the idea was due to Stuart Baldwin, but it was Mitchell who worked this out, and this is a typo. These two pluses should be in the exponent. And the idea was just not to worry about this issue. Just if these measures happen to be partial, just keep them partial. But whenever you are facing the task of forming an ultra power, just truncate this model back to the longest initial segment to which the measure is still total, and then form the ultra power of that initial segment. Yeah, if you think about it, this looks like something ridiculous because you are discarding a lot of information. So I think the entire magic of the thing is that it doesn't matter. And hopefully I may be able to explain why. And so Mitchell just built these models up to order of kappa is kappa double plus, and around the same time Jensen did it up to one strong cardinal, which I will recall what it is. And yeah, now we cannot any longer assume the kind of covering lemma for these kind of models we had before. Yeah, again, because measurable cardinals can be singularized, and also once we get to this region, one can force the failure of SCH. Yeah, so this is kind of the maximum, like, general result one can get, which is called the weak covering theorem. And this is a little bit technical. Yeah, so if you have a cardinal of k, then its cardinal successor, compute the cardinal successor of this cardinal in k and compute its cofinality in V. That is big. Yeah, it's bigger, at least as big as the cardinality of kappa in V. And still, if kappa is a singular cardinal of V, that still gives you that the k computes the cardinal successor of this correctly. But there are much stronger covering theorems, but they involve what is called indiscernible sequences, which were first analyzed by Mitchell for his core model, and then later Gittig and Mitchell had a detailed analysis in the core model up to a strong cardinal, and they gave a very detailed characterizations of the failure of SCH. Yeah, in terms of, like, they calculate exactly how much you need to be able to force to violate SCH. So that's roughly the rough history for models up to strong cardinals. So let me now recall what extenders are. And so if we go back to measures, this is all we can do with measures. Yeah? If we form an ultrapower, then the model M is generated by the range of the ultrapower map together with a single point kappa. Yeah? Every element of the model of the ultrapower can be written of the form image of some function applied, and then we apply that image of function to kappa. Yeah? And that's precisely, the object represented by function f is exactly the object which you just take the image of the function and apply kappa to it. Yeah? And this is the maximum agreement you have. Yeah? So the ultrapower agrees with V up to kappa plus 1 included, but not further. Yeah? So you can strengthen the properties of embedding by doing two things, which actually are very closely related. Yeah, you just increase the agreement between V and the target model. Yeah, so you may require that some V alpha for big alpha is contained in the ultrapower. So that would be called strength. Or you will try to find a way of building an ultrapower which is generated by more than a single critical point. Yeah. Yeah, so an embedding is beta, so that's exactly what it is. So an embedding is beta strong if and only if beta, V beta is contained in the ultrapower. So rank initial segment of height beta. And an embedding is strong if and only if it is beta strong for every ordinal beta. I think Menachem mentioned this. Sorry?
A particular J cannot be strong.
Yeah, sorry, yeah, so that's actually wrong. I say cardinal is, yeah, this should be crossed out, yeah, thank you, yeah. Yeah, the cardinal, this cannot be beta strong for every ordinal beta because of Kuhnen, of course, yeah, so. So this should be, again, there should be kappa and not J. Yeah? So and when I say A strong, A reflecting, by that is meant that when we stretch the set A, then the intersection, the stretching of A is the same as A all the way up to rank initial segment of beta. Yeah? So this is, yeah, so this, okay, so this should be rewritten. A cardinal is A strong if and only if for every beta we have an embedding which is beta A strong. And the point is, yeah, again, yeah, those are proper class embeddings, but the point is that similarly as we did with measures, these can be coded by set size objects. And these are called extenders. Yeah? So if we have an elementary embedding with critical point kappa, and this beta should be smaller than j of kappa. So that's image of kappa. So that's another typo. Then we just can derive a measure on the set of finite tuples of the same size as kappa. Yeah? And yeah, so what the extenders I'm going to talk about are much more modest than the ones Woodin is talking about. So this those are the simplest. So what he called space, that's just the space is just this kappa. Yeah. In my case, in his case, it may be much more. Yeah. So these embeddings look like this. There is kappa. There is j of kappa, and my beta is here. Yeah? And what is an extender? Then a kappa beta extender is just the collection of these measures. Yeah. So that's one definition. So we say that this will be then the extender, kappa beta extender derived from J. There is an alternative definition due to Jensen which is just, you can think of extender just as just the map which you get by restricting of this J. Yeah? So you look at this map Ex, which to each subset of kappa x assigns J of x intersection beta. That's enough information. So essentially, all you need is something that will enable you to run the ultra power construction. So it's either this or this. And of course, these measures are kind of coherently embedded into each other. So let me just briefly say, yeah, we will have these projections, yeah, if A and B are finite subsets, one in the other. So the projection from kappa to the size of B to kappa to the size of A is just to each, yeah, what it does is to each set here, you just look at how A sits inside B, and then you do the same thing with each element of this set. Yeah, so this value sits inside you the same way A sits inside B. And instead of this, I will write UBA. Yeah. And similarly, we can also, if we have pick an ordinal inside A, then we can look at how the ordinal sits. Yeah, and then we can write down a function which does the same with the tuples of the same size. Yeah. And yeah, so this is not, I don't want to read this in detail, but it just, I mean, as Hugudin said, it doesn't really matter what you write down, but this is just the important thing is that it's just a finite list of properties which you need to be able to run the ultra-power construction, yeah? So alternatively, you can define an extender as a sequence of measures indexed by finite tuples in beta, yeah? So I said before, I had it on my slide before, I believe, these beta ordinals from beta are called coordinates, yeah? Each E alpha is a kappa complete ultrafilter. They cohere, and then we have the normality here, which I explain. It's a complicated, it looks a complicated formula, but I explain what it is for, so we don't need to read it in detail. The only point is that if you look into the books, authors usually include the requirement that the ultrapower is well founded. I'm not including it, and the reason is that we are going to deal, so we were dealing with M ultrafilters, so we will deal with M extenders, and we will need to characterize extenders internally, and the well-foundedness of the ultrapower may not be characterizable internally, so that's why I'm leaving that out. And then we just do the ultrapower construction. And again, I don't want to go to details, but I just want to point out what the main feature is. So if we had a measure, then the objects in the ultrapower were represented by a function. Here, the objects are represented by a pair, yeah? So A is this finite tuple of ordinals below beta, and F is a function which maps finite tuples in kappa which have same size as A into V, yeah? And then we just need to say when two such things are equivalent. So that's the formula, yeah? So we have to go to some bigger tuple which is common to both, and then we just look at the corresponding projections and ask the question whether the values are the same in a measure which is a join above both measures, yeah? So I think what is important here is to just to see that there is a way of saying, reasonable way of saying when two functions agree frequently, yeah? And so we can write down this definition and prove that this is an equivalence relation, mod out, and we denote the equivalence class this way, in squared brackets. And that will be an object represented in the ultrapower represented by the pair AF. And we get a wash theorem, yeah? It's similar, yeah? We just ask, on the one hand, we ask what is true in the ultrapower, yeah, at these objects, and then on the other hand, we look at what is happening in the model we take the ultrapower of, and again, we just look at the values of the functions, but we go to some big tuple which is common to both and look at the corresponding projections. Yeah? And using that, we have an ultrapower, that's the ultrapower embedding. Yeah? It's again defined using the constant function, and it doesn't really matter what you put here. You can put any set and the corresponding constant function. Yeah? But these properties are important, so the critical point is kappa, then kappa is mapped onto something which is at least beta, and the pair represented by AF is exactly the thing what we get by first calculating image of F by the ultrapower map and then applying to A. Yeah? And this is the important thing. This is how you represent ordinals below beta in the ultrapower. Yeah? So it is almost like taking the identity map here. Remember, if we have a normal measure, the critical point is represented by the identity function. So this is a generalization. Yeah? So ordinal alpha is just represented by singleton alpha and this projection. Yeah? And to prove this, we need this complicated normality condition. Yeah? So that the purpose of the normality condition is just have this. It's just to have a very simple representation of ordinals below beta. Yeah, and using the wash theorem, yeah, if we have the map, if we have a map J and we derive an extender from that map, then using wash theorem we can again embed the ultra power into the target model of J. Yeah? And I didn't write, so the formula is obvious. Yeah? So K of AF is just J of F applied to A. Yeah, so that's similar as we had before, if you remember. What we get, and I want to point out, yeah, so before we had that this was elementary and the agreement was including critical point kappa. So what we have something better here. Yeah, the agreement goes all the way up to beta. So this map is the identity map on beta. Yeah. Yeah, and because of this, yeah, let me just recall, yeah, because we can do this, then ultra power is generated by the range and now all ordinals below beta. So if this map happens to have that property, then that's already the ultra power map. Yeah, then N is the ultra power and this is the identity map. So this way you can generate more complicated maps than just using measures, and actually these maps are sufficiently complicated that you can do a lot of interesting stuff with them. Yeah? I guess you wouldn't introduce the notion of generators, so I will introduce it also, so that will be a little bit of repetition. Yeah, so, and it again, because we are going to use it quite heavily. So again, so what are generators? You see, if we go back again, it's this property. Yeah? The ultra power is generated by the range of the map together with these ordinals. You may not need all ordinals smaller than beta to do this. So generators are just those ordinals smaller than beta which you must use in order to generate the ultra power. Yeah. And how do you determine them? Well, you just go from the bottom, and each time you see an ordinal which is not generated from the previous one, that will be your generator. Yeah. So Xi is a generator if and only if it is not of this form. And I am, you see, you may say, well, I am not being precise because I defined this for finite tuples, but actually one can show that this is equivalent. So I'm just making the definition a little bit easier. Yeah? So a generator is anything which cannot be represented in the ultra power by a smaller. And there is some kind of sloppiness in this notation, you can see. So this is more correct. So the least generator is a critical point. And if an extender has only one generator, then it is basically a measure. But if it has two generators, then it's already its consistency strength goes past order of kappa is kappa double plus. So that's kind of a big jump. Sorry? Yeah, okay, that's true, but it's a fake extender. Yeah, you are right. But I will explain. So these are, I'm talking about extenders which are not stretches of an extender. Yeah. So that kind of extender. So those would be extenders which are allowed to be on an extender sequence of an inner model. So then the one you mentioned is not allowed to be there. Yeah. So. So the natural length, yeah, so I should be more precise. I mean, so this is not entirely precise what I'm saying, but say all extenders of our interest here. Yeah. Yeah, and so the natural length of extenders is just the strict supremum of all generators. Yeah, so I look at all generators, add 1 to each of them, so it's just the smallest ordinal which is strictly above all generators. Okay. And I was only talking about extenders in V, so now going to M extenders is the same as step between ultrafilters and M ultrafilters. So everything translates literally. Yeah. So what the difference is, we only demand that A. So if A is an M extender, then we only demand that A measures subsets of the critical point which are in M. So each of these, that should be E sub A here. So that's a typo. Is an M ultrafilter. The normality condition only applies to functions in M, and when forming the ultra power, we only use functions from M. Yeah? And also, you see, the notion of generator is also defined using some functions, so those functions should be also taken from M. So whatever, when we talk about M extenders, all relevant functions must come from M, but that's all the difference. Yeah? And the weak amenability, yeah, remember, an ultrafilter was weakly amenable if it didn't add any new subsets of the critical point when we formed ultra filter, yeah, ultra power. So the same here, yeah. We can literally copy the definition, and one can show that that's equivalent to the demand that no E sub A is adds, that each of these ultrafilters is weakly amenable. Yeah, so, okay, and then when I write this, I mean that we restrict the coordinates to gamma. Yeah, so, and then now we are going to build inner models, and so we need we need to make the extenders a little bit longer than their natural length. So we are going to add some fake information. And so those are those two completions. I mean, I will be mainly considering Mitchell-Steele completions, yeah. So, which are also called trivial completions, yeah. So what is that? Yeah, so this is probably a bit misleading, yeah. So, but what I mean is, well, take an extender, form the ultra power, and look at the cardinal successor of the natural length inside the ultra power, and then derive an extender of that length from the ultra power map. Yeah. So this may not make sense if E has length, if the coordinates are just below nu E, if it is too short. Yeah. But basically, what this is, it's just this extender which has the same, which carries the same information as my original extender, but its coordinates are this big. That's the point. So we just go to the first cardinal above so the coordinates are just the first cardinal above the natural length inside the ultra power. Why that? Because we want to get to have coherence, yeah, and so this thing is just designed to have coherence. Okay, yeah, and now think that we are going to build model from extenders. Yeah, so we are going to use the constructible hierarchy, and every little while we may have an extender at hand which we are going to put on the hierarchy. So we are going to build a sequence. Yeah. So the stages where we are putting extenders are these indices, yeah, and the extenders themselves will be values, yeah. So really, what we are going to do, we are going to construct relatively to some class which is just a function which to each limit beta assigns some object a beta. It will be an extender, and as Hubudin mentioned yesterday, it will not be literally an extender, but it will be just something which codes an extender. Because it may happen that if we put an extender there, then it wouldn't get into the model. So we just code the extender by small objects which have chance to get into the model. So it's a technical thing. But notationally, we will not distinguish between them. Yeah? And so if we have a structure built constructively from such a sequence, then when I say initial segment of length beta and denote this way, then I mean just the structure which is constructed all the way up to beta, and then the beta value put here as a predicate. So in other words, we cannot, when we talk about initial segments of length beta, we cannot forget about this predicate which is at omega beta. Again, this omega beta will be mostly beta. Whenever this will be an extender, omega beta will be beta. So I'm writing this only to be kind of precise, because the ordinals, remember, ordinals of these things are omega beta. And luckily, we have, you see, this was this crucial property that was in L, that if I compute the power set of the hierarchy and look which sets from that power sets are in the next step of hierarchy, those are exactly all sets which are definable over JA beta with parameters. This is crucial to be able to run fine structure theory. So luckily we have this here. And why? Because this is beta, and so because J beta has height omega times beta, and so the next level has height omega beta plus omega. And we are not putting anything from that predicate A here. So here we just do the constructible, just the rudimentary function. So if we put infinitely many points of the predicate A into this interval, then this bottom part would have never chance to know about this. So that would be false. But it's just this particular construction which makes that possible. Okay, and so with this notation, I can now define what a premouse is. So the definition looks horrible, but I have a picture which hopefully clears it up. I mean, it's easier to see the picture than this. So what is? So again, it is an acceptable structure. And let me just say, I was putting this index here. I'm going to put it now here as I will write it as a value of the function for some reason, because I'm going to use some notation later which may conflict, just to avoid misunderstanding. So this is just the top predicate. And so so we are constructing, we are constructing the hierarchy from below. At each limit step, we either add an extender or add nothing, the empty set. So each limit step, either on top of this thing, we either have an extender or something which codes an extender, or nothing. But if it codes an extender, then it has the right form. If beta codes an extender, then beta looks like this Mitchell-Steele index. So we call it the Mitchell-Steele index, this cardinal successor of the natural length in the ultra power. Then we require coherence, and coherence means that whenever we have a measure, whenever we have this extender and we form an ultra power of the original hierarchy, then the ultra power hierarchy agrees with the original hierarchy all the way up to the index of the extender. And the index does not index any extender any longer. So and the latter will be automatic if we have, because there is going to be one more condition which is on the next slide. So yes. So those two extender sequences agree. If I form the ultra power using this E beta, those two extender sequences agree up to this point. And in this structure, this ordinal does not index any extender. And that's so the name coherence is, I guess, appropriate for this. And then there is a fine structural part, so that makes the, this is what will give us continuum hypothesis and other things. Every proper initial segment must be sound, We said this is true in L. In these models, this is not automatically true, but you have to arrange it, so that's the task. And then there is something which is called initial segment condition, and it's a bit complicated, but let me just say what it tells you, that if you have an extender on the sequence and look at the initial segment of that extender cut at a generator, then that initial segment is also on the sequence. You would like to have it on the sequence, but you don't always can have it, so you have to allow this other option. The point is that you want this to be an element of your structure below beta. And so this is a stronger version. So any properly smaller piece of the extender is already inside your structure and actually on the sequence or very close to, or you are just one ultra power away. And this is almost always possible, but there are some extenders which are pathological and they cannot be extenders of any Primau sequence, so you have to rule out those. And this is the condition what when Moti objected what I said before. So if you have this kind of extenders, then it is true that such an extender with two generators already gives you O kappa is kappa double plus, because this rules out Moti's counterexample. So this is your picture. So I have three extenders here. So the red one has more details. That's the top extender. Alpha is the height of the structure. The top extender is not an element of my Primau's, but it's just a predicate on it. So I have a critical point here. Tau is a cardinal successor of the critical point in that Primau's. Here is my soup of generators. That's always bigger than tau, bigger than or equal to. If there is only one generator, namely kappa, then nu is equal to tau. And then I can have extenders here, which just, I may have an extender up here that wouldn't overlap with the red one, but now I can have extender which overlap, and those are two kinds of overlaps. When you have overlaps, then your situation gets more complicated, because you immediately are getting strong cardinals. If you think about it, from the initial segment condition, you will get, for example, that this, there will be a lot of generators here. If I cut, there will be cofinally many generators below kappa alpha. So if I cut this green extender at each generator, then that initial piece will be inside the model below kappa alpha. So if I cut the model below kappa alpha, then that initial segment will believe that kappa gamma is a strong cardinal already. So overlaps bump up the large cardinal strength a lot. Okay, yeah, so and that's, okay, now comes, so there are some things which happen, namely now I will need to do fine structure, not that I would like to, but for certain things we don't know how to do them, at least at these levels, and then I would like to take ultra powers, and we said that we need an amenable structure for both. This is not amenable in most cases. Yeah, so that's the first problem. It's just a technical problem because we can translate this into an amenable structure. So basically what you do when you work with these things, you just translate to the amenable structure, then you do what you would need to do, and then you translate back. And then the initial segment condition has this awkward formulation, and that you cannot avoid either, because you can show that if you want your sequence to be rich enough, then you always have these pathological extenders. So you just have to live with them, which makes the life a bit more unpleasant. And this, okay, and I said that the one extender which is indexed at the top is called the top extender. Okay, now the next thing, so far we did just, in this example with zero sharp, we did just ordinary ultra powers, and we will need some, and those ultra powers had just the property that the maps was sigma 1 preserving. So we will need to increase the degree of preservation of these ultra power maps to be able to work. So we will need to do something which is called fine ultra powers, and I'm not going to say exactly what it is, but I just how they are constructed. Well, we just take a little bit bigger class of function to represent our objects. Yeah. So I see. So before I go to that, let me just recall that we have to translate between amenable and non-amenable, and that works. Yeah. So if I want to form an ultra power of M, we translate M to the amenable variant, then form the ultra power, and one can show that this ultra power is just a head structure of some primals. Yeah. So we can translate back. So this translation between amenable and non-amenable is reasonable enough to enable doing this, and I will now forget, so whenever I talk about ultra powers, I will not distinguish between head and non-head. So I will just write the things without head, and I think I have that somewhere on the slides. Yeah. So each fine ultra power is assigned some degree number, and that's the degree of the ultra power, and that will give you the degree of preservation of the map. Yeah? And so, yeah, these are built using some functions which are n-definable, if you remember what that was, over M, but only certain specific ones. Yeah? And really, yeah, for what we are going to do, we don't need to know exactly how they are defined. What we need is the following, that, and I have it maybe on the next slide. No. Yeah, it's here. Yeah, that the ultra power map, the n-ultra power maps is an n-embedding. Yeah, so it has this higher degree of preservation, and it's exactly matched. Yeah, so it preserves all statements at the level n. It preserves canonical and Skolem functions. That's all what we need to know about it. Yeah. And just a remark, so these ultra powers we use to look at zero sharp, they are actually fine structural. They are zero ultra power. but we didn't know about at that time. Yeah. So now, what is important is that the n ultra power can be only formed for n such that the nth projectum is about the critical point of the extender. So we will usually take the n to be maximal such, and so then we talk about maximal ultra powers. Yeah? And so in our case, this 0 ultra power was maximal ultra power, yeah, if you think about it, because the first projectum was already omega. Okay, so I have 1 minute. So let me just say something about iterating ultra powers. So I just start with a very, very simple case, linear iterations of total extenders. And then you just do what you expect. You start from your pre-mouse, and then at step alpha, you just take the maximal ultra power of what you have. Yeah? You pick an extender from M alpha, form an ultra power of M alpha, and you get M alpha plus 1. Yeah? And the remaining embeddings are obtained by composing, and at limit steps we take direct limits. And we say that the linear iteration is normal if each next critical point is at least as big as the natural length of all previous extenders. So yeah, so your critical points go up quite fast. And why is this important? Because the normality is crucial. If you do this, then you can reconstruct the extender from the iteration map, right? Because you basically your iteration map look like this. You have an extender, and then you have your next map has critical point above. Yeah, so you can reconstruct this extender from this map, but because this map is the identity here, you can also reconstruct this extender from the entire map. Yeah, because that's what it says. Yeah, X is inside the 8th measures of alpha extender, if and only if A is in the image of that set. Yeah, but the image of that set is not moved by the map, by the rest of the map. Yeah. And this is very important for the comparison argument. So let me just say the comparison argument, and then I will stop. Yeah. So for the moment, just assume that the extender sequences are non-overlapping. So you don't have these patterns I had before. Yeah? You don't have these patterns. So the next extender would be here. So they are kind of nice. And so a padded iteration is just something that it allows steps where we don't do anything. And that's because what we are going to do, we are just going to take 2 mice. Then we look at the smallest disagreement. So the smallest ordinal such that the 2 extender sequences are different. And now there may be extender on one side and nothing on the other side. So what we are going to do, we are going to form an ultra power on the side where we have the extender, and we are going to do nothing on the side where we don't have anything. Yeah? So that's padding. Yeah? So that's padding means doing nothing. And then the map, so we just let the next model to be the same and the map be the identity. And so the comparison is the following. Yeah? So suppose you have 2 such mice, and you can suppose they are iterable and have non-overlapping extender sequences. And then take a lambda, which is a regular cardinal, which is bigger than cardinalities of those 2. And then this comparison process, which I just described, stops at some point which is strictly smaller than lambda. That is, we just, after repeating these iterations by least disagreement, in less than lambda many steps, we reach 2 models such that one of them, or the extender sequence of one of them, is initial segment of the other one. Yeah? So next time I will sketch a proof of this, because that proof is important and is very similar to the proof we did when we showed that 0 sharp is unique. Yeah? And then we introduce iteration trees. And what's the point of introducing iteration trees? Well, the point is that we had this non-overlapping here, and that was important because the non-overlapping sequences generated iterations with this property which we had before, yeah? That the index of that these iterations were normal, so each critical point was bigger than sup of the natural length of the extenders used before. But of course you don't have this in general, and so if you try to do linear iterations, you will be forming ultrapowers with all kinds of critical points, and then that will ruin this argument. So the point of iteration trees is just to make the comparison argument work. So that's where I will start tomorrow then. You get an extender which carries the exactly same information, yeah? As long as you are at least above the sup of generators. So in other words, they may have different lengths, but if you now form ultrapowers using each of them, the ultrapowers will be the same.
Okay, so is it always the case that if you have some embedding derived to the extender, and go back to the embedding, you get the same thing back? Or do you sometimes get a different embedding as you would if you derived an embedding from an ultrafilter and then derived the ultrafilter?
I'm not sure I understand all details. So you start from...
Maybe I've said things the wrong way around.
So you start from an extender or from an embedding?
From an embedding.
You start from...
An extender or ultrafilter?
Yeah, so you start from an embedding and you fix your beta. And you derive kappa beta extender from the embedding.
Yes.
Then you form the ultrapower.
Yes.
You get the ultrapower map.
Yes.
Then you derive kappa beta extender from this ultrapower map.
No, then you
No?
look at the two factors, the one you started with.
It's in general different, yeah.
Okay.
But remember, okay, this is I should have said it more explicitly. But I think it was on this slide, yeah. But if this map, so you see this map can be very wild. So really another way of thinking about these extenders is that you see if you look at an extender, so if extender is E with critical point is kappa, then the relevant information for forming ultrapower is here in H kappa plus. So this extender somehow gives you how this is mapped, but this corresponds to V kappa plus 1. Yeah? Let me probably but then the ultrapower determines uniquely what happens here, how these things are mapped. But you may think of that you will have another embedding which up to V kappa plus 1 is the same as the original one, but here some horrible things happen. Yeah, a lot of discontinuity points. Yeah? Basically, if you take an extender here, then all cardinal successors above are continuity points. Say if you have GCAs. Yeah. But
one extender when you take.
Yeah.
You take the embedding from essentially.
Yeah. So you can.
Root of power 2.
Yeah. Yeah. So you can do some extend, followed by some extender here, and that will ruin the thing. So the ultra power embedding is, in a sense, the smallest of all embeddings. That's what this picture tells you. Yeah. Whenever it can be embedded into any embedding which agrees on this bottom part. Yeah? But if this J happens to be a small embedding, namely if the model N is generated by all of these things, then already it's the ultra power one. Yeah? Okay. Yeah.
How difficult is it in general to compute, say, the natural length of an extender? So, like, the simplest case, say that I take a theta strongness embedding, then the generators will be contained in that theta.
Yeah, it's. Yeah. Oh, sorry. So I was supposed to repeat the question. So, what would be the strength? What would be the natural length of an embedding whose strength is theta? I have to say I don't know on top of my head, but yeah, this is something related to the size of the strength. Yeah. I don't know. Is that good enough? Or you can. Yeah, you can. But yeah. Probably. I have to say, I haven't thought about it. So whatever I would say would be probably wrong if I try to calculate it fast. Yeah. But you see, there is. Yeah. But it is true that you can always. Maybe that's one thing I should point out, because I only defined extenders where coordinates are ordinal. So you can define more general extenders where coordinates constitute are say in some V alpha. Yeah. But you can capture those extenders using extenders from ordinals because you can do some coding. Yeah, so. Thank you.
So this concludes this today's session, and I heard about some reflections.